Well, hi again, this is Bob, and I mentioned in my first lesson on 5.4, the multinomial distribution, either something's going on with Blackboard or I'm using a different internet connection while I'm talking about this last lesson here. So I've decided to break 5.4 into smaller parts. It's very frustrating to go through and maybe lecture for 45 minutes or so and then find out you lost everything because of a loss of connection. So we just finished the multinomial, and you may recall that section 5.4 discusses 4 other probability distributions, and each one of them has something to do or is built on something that we've seen before. It's sort of an enrichment section, and I thought it was important for 2 reasons. One, so we get a little feeling a little more confident and good about the different probability distributions and knowing a little bit extra. And then, of course, some of you are going to go on and take other statistics classes in which these, I'm sure, will appear, and you'll have a foundation to build on for maybe a more extensive look at these distributions. Anyway, we're going to talk about the Poisson distributions, and the first thing that they tell us is that we can use this when we have a large N or population and the probability is small. Okay, and very important, our independent variables occur over a period of time. Now, they give us a couple of examples of what they mean by that, and of course, I know that you'll be doing some careful reading here. But for example, they say we use it when we have a density of items is distributed over a given area or volume, such as the number of plants growing per acre. Okay, well, remember, plants per acre is like a rate, okay? And they give us another one as an example, like the number of defects in a given length of videotape. There's another one we'll see in a minute, another use for this. And of course, there won't be any confusion when we get around to a quiz or a test or something like that, because like everything, and this is a feature that I like so well about this book, they're going to tell us the distribution to use or give us an example. And of course, the questions that we're going to have involving the Poisson distribution will be coming up directly in section 5.4. And what I'd also like you to recall is just this is just an introductory lesson. I'm going to do 2 examples and then move on. And if you look at the very bottom of page 291, they give us a formula there for the Poisson distribution. It's something like probability of X, and then they use a semicolon, and then they have this Greek letter lambda. And then if you notice, the formula starts off with something that, unless you've had Math 105 or at least 107, you may not have seen before. Well, at least we see some things we have seen before. We see the x factorial in the denominator, and we see the x as an exponent. But again, recall that we only want the introduction to this and work a sample problem, get the feel of it, and move on. So we're not going to use the formula. It's nice for us that we have Poisson tables for the formula, and they start on page 776. So I'm going to write a big note here to use the tables that begin on page 776. So there's no formula work, and as I mentioned, some of you may not have been exposed to E, the natural log, before, okay? Or base E, if you will. Excuse me. Anyway, here's what I'm going to do. I'm going to work example 528, and the first thing I'd like you to notice, this is a very short lesson, is look up on the top of page 292, and if you notice, we've got our random variable x, and then we've got some table with lambdas. We'll see about lambda in just a second. And they've shown us that to find the lambda for an x random variable is 3 and a lambda of 0.4, that we can, as we've done so many times with tables before, go down and across, and we get 0.0072. Okay, that's a lot easier than working that equation they just gave us, or formula, that involved the natural log, or base e. Anyway, we're going to do two examples, and the first one is example 528. And this is a typical problem where we've got a density distributed over a period of time. Or length, if you will. And the idea is that you can use a lot of different words to describe this, but there are 200 typographical errors that are randomly distributed in a 500-page manuscript. Find the probability that a given page will have exactly 3 errors. Excuse me. So here's the idea. The first thing we have to do is find lambda, and that's the average number of errors per page. That relates back to the just the previous page, the average plants per acre, or the average defects in a given length of a videotape. And so if we have 200 typos distributed over a 500-page manuscript, that'd be the same as 2/5, or lambda equals 0.4. That would be our mean number of errors, or in this case, lambda. So we're half done. We're all the way done, because we're going to use the tables. And remember that remember to get into the tables, we need this. And so in this case, it would be exactly 3 typos with a lambda of 0.4. Now, so that means that we would go back to page 776, where the lambda tables start, or where the Poisson distribution tables start, and we would look up, just like we did. In fact, it's no coincidence that on the top of page 292, I'll just remind you again, we had our random variable x and 3 down below, and for our lambda, our 0.4 was about there. And we went over and down, and we came up with 0.0072. And that's our answer. That's the probability of finding exactly 3 errors on a given page, given that there were 200 typos randomly distributed over a 500-page manuscript. That is all we're going to do with regard to this type of question. We're not going to use the formula. We just want to explain what the Poisson distribution involves and how we can use the Poisson tables to get an answer. Okay, well, there's one more use of the Poisson distribution, and that is, I'd like you can take a look at example 529. Excuse me, but we're going to look at example 530 now. And the idea of 530 is it relates, this is the in the middle of page 293, it relates the Poisson distribution and the binomial distribution. Okay, and they tell us that the Poisson distribution can be used to approximate the binomial distribution. Now, you're not going to be asked to do anything. In other words, there will never be any confusion if you are asked. You'll never have to decide which one to use. Okay, but I am going to give you a test question that asks you to approximate the binomial distribution using the Poisson tables, but you won't ever have to decide, or said differently, you'll always know which table to use because I will instruct you to. Okay, there's a requirement though in order for us to use the Poisson distribution or using it for a probability, and they tell us that n times p must be less than 5. Excuse me. This is again on the middle of page 293. Now we're going to figure out lambda by taking the number of trials times the probability, and I don't know why I wrote p there. NP must be less than 5. And that's the same as saying NQ must be less than 5 if we're using that. Okay, so let's take a look at this left-handed question on example 530. And here's what they tell us. You have a room of people, 200 people, and approximately 2% of those 200 people are left-handed. Find the probability that in that room with 200 people, exactly 5 are left-handed. And in this situation, to find our lambda, we're going to take n, which is 0.02, 2%, times the 200 people in the room, and it comes out to exactly 4. In other words, we would expect 4 people in that room of 200 to be left-handed. Okay, so there's our lambda, and that's the way we find it in that situation. Okay, oops. Now, what we wanted to find out is exactly 5 people. So 5 becomes our random variable with a lambda of 4. Okay, and they tell us, now what they've done is they've used the formula, but remember, we don't want to use the formula. Okay, the formula isn't necessarily above us. There's just no reason to use it when we can go back and look at the tables. And when you go back to the tables that start on page 776, remember this is our random variable and this is our lambda. When we use the tables, we end up with 0.1563. Okay, which agrees with the answer that they got from using the formula. Okay, then to close off this lesson, they reminded us that we could have also done this question the long way by using the binomial distribution formula. And by the way, remember we're talking about 2 things. A person's either left-handed or they're not. They're right-handed. So that's a binomial type situation. They tell us that we could have found the exact same answer by going 200 combination 5 times the individual probabilities of 0.02 and 0.98. And we wanted 5 of those people to be left-handed in the room, and that would leave 195 of them to be non-left-handed or right-handed. Okay, and when we work this question out, this way we ended up with 0.1579. Well, that is very close to 0.1563. And they tell us that the difference there was just some rounding from the formula. Okay, this is more than enough to introduce a Poisson distribution. We know that we can use it to find the density of something spread out over an area, like plants per acre, or typos per so many typos per so many pages. And we know we can use it to approximate the binomial distribution. So I'm going to stop there and again cross my fingers that I didn't lose my connection or have any problems on this. And I'll be back shortly with our next one. It sounds like it's really involved. It's called the hypergeometric distribution, but it turns out we've done something like it already. We're just adjusting some things and using a different name. So I'll be back shortly with the hypergeometric distribution. Thank you.